We have an example problem here. A low-cost way of sending spacecraft to other planets would be to use the radiation pressure on a solar sail. The intensity of the sun's electromagnetic radiation at distances near the Earth's orbit is about 1,300 watts per meter squared. What size sail would be needed to accelerate a 10,000 kilogram spacecraft towards Mars at 0.01 meters per second squared, which is an incredibly small acceleration, of course. So it would take a very long time for this to be the only power source to move this sail. So let's visualize this a little bit. So we have the sun emitting light in all directions. This sail, we're assuming, is out near Earth's orbit. So Earth's out here. We have a sail, which of course is not drawn to scale. The reason I'm putting my sail at Earth's orbit is because the problem tells me the intensity of the sunlight is approximately 1,300 watts per meter squared out here. All right. What size sail would be needed to accelerate? So we have a 10,000 kilogram spacecraft. We're wanting to accelerate it at even just this small acceleration of 0.01 meters per second squared. Well, mass times acceleration, hopefully this brings back Newton's law. We're going to look at assuming just the force of the sunlight is causing this force. So no gravitational pulls. We're not accounting for anything like that, which of course wouldn't be the best assumption either. But for the the sunlight itself to exert a force of 100 newtons on this sail. All right, so radiation pressure is where force is going to come into play. The force on this sail divided by the area of the sail, that's the radiation pressure, that needs to equal the intensity of the sunlight divided by the speed of light. This, of course, assumes that this sail will perfectly absorb all of the energy. And again, we're making that assumption because that is the equation our author has chosen to focus on. So we know the force on this sail / spacecraft because we know the mass of it and the acceleration is what they've given us. We've been given the intensity of the light, we have the speed of light, so we actually can calculate the area, at least, force times speed of light over intensity. So 100 newtons times the speed of light over our intensity. So the area .308 times 10 to the 7th meters squared. My brain, this doesn't mean a whole lot to me, though we're technically would be done. Let's assume, just because I want to put this into a context that I can make sense of. So let's just say this is a square sail, so sides of x. If this is the area, then I would set that equal to x squared. So if this happened to be a square cell, oh wow, which we can't be this accurate. This would be approximately 4,800 meters on a side. So what, that's 48 football fields approximately on a side. Not very practical, of course, but looking into harnessing energy from the sun and contributing to motion is a good thing. It's just not going to be the practical only way to go about it, at least not in this particular way.